I just bought a Subaru Crosstrek. I would have bought a Lambo, but I'm not quite there yet. Sometimes I get drunk and I forget what day it is. I wish that I was skinnier, but I love sandwiches. One time I tried to...
Now that we've proven that z mod pz star is cyclic, we can use this fact to understand z mod nz star in general. So our goal in this video is going to be to prove corollary 20 in section 9.5, which says that if n is a positive integer at least 2, and it has prime factorization, n equals p1 to the alpha 1 times pr to the alpha r, where these pi's, p1 up through pr, are distinct primes, and each one of these alpha i's is greater than or equal to 1, then we can write down the structure of the group of units of z mod nz star in terms of these prime power factors. So the first statement is z mod nz star is isomorphic to z mod p1 to the alpha 1 z star cross z mod pr to the alpha r z star. So it's enough to understand the structure of these, the group of units of a prime power order cyclic group. Okay, so that we actually already knew. That's something that we talked about at the end of our discussion about the Chinese remainder theorem. And I'll say a little more in a second. But what's the new part is now let's just look at each z mod some prime to some power z star. Well, if your prime is 2, then we need to know what is z mod 2 to the alpha z units isomorphic to. And we'll see that this is isomorphic to z mod 2z cross z mod 2 to the alpha minus 2z for all alpha at least 2. So we know that this is a finite abelian group of order 2 to the alpha minus 1. And we know that it's not always cyclic. For example, we know that z mod 8z star is isomorphic to z2 cross z2. So just to check, when alpha equals 3, you get z2 cross z2. And OK, what if you have an odd prime? Then the fact is that z mod p to the alpha z star is cyclic. It's a cyclic group of order p to the alpha minus 1 times p minus 1 for all odd primes p. So not only is z mod pz star cyclic, but z mod p squared z star, z mod p cubed z star, the group of units of this prime power order cyclic group is always cyclic for any power of an odd prime p. OK, so let's prove this. The first statement, this was corollary 18 in section 7.6. We talked about this when we talked about the Chinese remainder theorem. The important thing is to show that the ideals generated by pi to the alpha I and the ideal generated by pj to the alpha j are co-maximal in Z. And that's true because their GCD is 1. OK, so Dummett and Foote give a lot of the proof of 2 and 3 as exercises. So this second statement follows pretty much from exercises 22 and 23 of section 2.3. But those exercises are actually pretty challenging. So they use some combinatorial things that we haven't talked about at all. So I'm going to give actually a slightly different proof that I think is more a little bit easier to check. All right, so what are we going to see? We're going to see that for alpha at least 3, 5 has order 2 to the alpha minus 2 in z mod 2 to the alpha z star. OK, so that's also what you do in exercise 22. But the advice there is to show that 1 plus 2 squared has order 2 to the alpha minus 2 in this group by using the binomial theorem. So you need something about divisibility of binomial coefficients by powers of 2. OK, so what is this going to tell us? Well, once we have an element of order 2 to the alpha minus 2, we know that when you write this as a direct product of cyclic groups, one of those cyclic groups should have order 2 to the alpha minus 2. That there's some element of order 2 to the alpha minus 2, and then there's like all the rest. OK, so what is the claim? We'll prove something stronger than the fact that the order of 5 in z mod 2 to the alpha z star is 2 to the alpha minus 2. We're going to prove that 5 to the 2 to the alpha minus 2 power, this integer, is equal to 1 plus some odd number times 2 to the alpha. Okay, we'll prove this by induction on alpha. When alpha equals 3, what are we saying? 5 to the 2 to the 3 minus 2 power, 5 to the 2 to the 1 power. So 5 squared, 25, is equal to 1 plus some odd number times 2 cubed. And that's true. It's 1 plus 3 times 2 cubed. Okay, so the base case, alpha equals 3, is fine. Let's suppose that this statement is true for alpha and prove it for alpha plus 1. So what happens when we put in an alpha plus 1 here? We get 5 to the 2 to the alpha plus 1 minus 2. Alpha plus 1 minus 2 is alpha minus 1. And if you take 5 to the 2 to the alpha minus 2 and you square it, you're raising a thing with an exponent to another power. So the exponents multiply. And you see that 5 to the 2 to the alpha minus 1 is 5 to the 2 to the alpha minus 2 squared. But we have an expression by induction for this thing that we're squaring. It's 1 plus n alpha times 2 to the alpha squared. You square it out. This is 1 plus 2 times n alpha 2 to the alpha times 1 plus n alpha squared 2 to the alpha squared. 2 to the alpha squared is 2 to the 2 alpha. And we can write this as 1 plus n alpha times something. Why would we do that? Our goal is to write 5 to the 2 to the alpha minus 1 as 1 plus n alpha times something. This is going to be a different number now, but that's the idea. So we'll take out this 1 and write everything else as a product. 1 plus n alpha times 1. So what do we get from this first term? Is it's n alpha, and then we have a 2 times 2 to the alpha, which is 2 to the alpha plus 1. We also have a 2 to the alpha plus 1 in this term. So we'll just factor out that 2 to the alpha plus 1. So we get 1 plus n alpha times 1 times 2 to the alpha plus 1, which gives us this second term. And then what's left over is we have an n alpha squared. So we have another n alpha, 2 to the alpha minus 1, 2 to the alpha plus 1. That gives us 2 to the 2 alpha. OK, so that's it. So this statement is true. But what does that tell us? Well, let's look at 5 to the 2 to the alpha minus 2. That is congruent to 1 mod 2 to the alpha. Just take each side mod 2 to the alpha. So the order of 5 in z mod 2 to the alpha z star divides 2 to the alpha minus 2. But the only things that divide 2 to the alpha minus 2 are smaller powers of 2. So let's just go down one power and see, well, what can we say about 5 to the 2 to the alpha minus 3? That is 1 plus some odd number times 2 to the alpha minus 1. So it's definitely not 1 mod 2 to the alpha. That means the order of 5 in z mod 2 to the alpha z star is exactly 2 to the alpha minus 2. OK, so we know that in this group we have some element of order 2 to the alpha minus 2. So now we only have two possibilities. Either this group is cyclic or it's not cyclic. And if it's not cyclic, it has to be z mod 2 to the alpha minus 2z cross something. And that something, the only thing it could be is z mod 2z. OK, so I'll pause and erase and then show you the remaining part of this exercise, which is how to see that this group is not cyclic. Let's finish this argument about z mod 2 to the alpha z star. All we have to do now is show that this group is not cyclic whenever alpha is at least 3. And the way that we'll see that it's not cyclic is by seeing that it has too many elements of order 2 to be cyclic. Right? If you're a finite cyclic group, then you have a unique subgroup of order d for each d dividing the order. So you should have exactly one element of order 2. It's contained in that unique subgroup of order 2. OK, yeah, I mean, another way to say it, actually, that's maybe better is we prove this thing that if you have a prime P and you have a finite group G, the number of elements of order P in G is the number of subgroups of size P times P minus 1. OK, so anyway, as long as we have more than one element of order 2, that means we're not cyclic. But based on what we just saw about powers of 5, 5 to the 2 to the alpha minus 3, that has order 2. Because you square it, and you get 5 to the 2 to the alpha minus 2, which is 1 in z mod 2 to the alpha z star. Same thing, -1 times this 5 to the 2 to the alpha minus 3. That also has order 2. Okay, and now -1 also has order 2. So here are 3 elements of order 2. So let me just note, you really do need alpha to be at least 3 because you want these 3 elements to be different, but they are. So okay, so this group has too many elements of order 2 to be cyclic. So we've seen that it has to have a subgroup isomorphic to z mod 2z cross z mod 2z. And once we know that we have a subgroup isomorphic to z mod 2z cross z mod 2z, and we have an element of order 2 to the alpha minus 2, that uniquely determines that z mod 2 to the alpha z star is isomorphic to z mod 2z cross z mod 2 to the alpha minus 2z. Okay, let's do the proof of the last part about z mod p to the alpha z star. All right, let's say p is not prime. The proof in Dumb and Foot refers to this exercise 21 of section 2.3, which again is a little bit tricky. It asks you to use the binomial theorem to show that 1 plus p has order p to the alpha minus 1 in z mod p to the alpha z star. So I think that's a little tricky. So again, I'm going to give you an argument that's a little bit different. You should think about how to use the binomial theorem to do this as well, what you would need to be true. And OK, so if we just believe this for now, then what does this mean? So since z mod p to the alpha z star is an abelian group of order p to the alpha minus 1 times p minus 1, if you have this element of order p to the alpha minus 1, that means the p-CELO subgroup of this finite abelian group is cyclic. So then what we're going to show is that, in fact, what do all the other q-CELO subgroups of this group look like? Well, they have to divide the order of the group. So those correspond to primes q dividing p minus 1. So for every prime q dividing p minus 1, we're going to show that the CELO q subgroup of z mod p to the alpha z star is also cyclic. And then, because a finite abelian group is a direct product of its CELO subgroups for the different primes dividing the order, if each one of those prime power order subgroups for these different primes, if they're all cyclic, then we've seen the direct product is cyclic as well. You can use the classification for finite abelian groups for that if you like, or we've also seen how to do this more directly. OK, so once we see that all of these CELO q subgroups are cyclic, then we'll be done. And we'll see that z mod p to the alpha z star, in fact, is also cyclic. OK, so we have 2 things to do. The first one is to prove this statement that 1 plus p has order p to the alpha minus 1. And I'm going to do that by proving something a little more general and then specializing it to the specific case of p plus 1. All right, so I'm going to prove this lemma, which says, let's define vp of x to be this function that gives you the largest exponent. This is going to be equal to the exponent of the largest power of p dividing x. So for example, if x is 50, then v5 of x would be 2, because 5 squared divides x, but 5 cubed does not divide x. But v2 of 50 is 1, because 2 divides x, but 4 does not divide x. OK, so what we're going to do is take an integer z that is 1 modulo p. And we'll show 2 things. One, that vp of z to the p minus 1 is equal to vp of z minus 1 plus 1. And then, by induction, using this first statement, we'll see that for all k at least 1, vp of z to the p to the k power minus 1 is equal to vp of z minus 1 plus k. So if you put in k equals 1, you exactly are getting part A. OK, so I'll pause and erase. We'll prove this lemma, and then we'll see how that gives us the order of p plus 1 in z mod p to the alpha z star. Let's prove this lemma. First, we'll prove B, the second part, assuming the first part A. And the important observation is just that z to the p to the k power minus 1 is z to the p to the k minus 1 power raised to the p power. minus 1. Okay, so now B follows directly from A by induction. And to really check that you believe that, you should just see what happens for k equals 2. Okay, so what is z to the p squared minus 1? It's z to the p minus 1. So what happens when you apply A now with your input z being z to the p? Right, so that's the idea. Okay, so now let's prove A. So we're going to write z equals 1 plus x times p for some x and z. And we can do this because we know that z is 1 modulo p. So what is vp of z minus 1? It's vp of x times p, which is 1 plus vp of x. Okay, so now what happens when we take z to the p minus 1? It's 1 plus x times p to the p minus 1. And now we can apply the binomial theorem. And okay, so we've canceled out the 1 to the p term because that's going to have a minus 1. So what do we get? We just get p choose 1 times xp plus p choose 2 times xp squared plus p choose p minus 1 times xp to the p minus 1 times xp to the p power. Okay, so what power of p divides the first term? P to the 1 is p. Xp certainly has 1 power of p because of this p, and then as many times as p divides x. So we get 2 plus vp of x, which is vp of z minus 1 plus 1. Okay, so now we'll see that the remaining terms are all divisible by higher powers of p. That the number of powers of p dividing every other remaining term is more than 2 plus vp of x. And okay, so we have a factor of x squared at least, and a factor of p squared at least in each of these. So we get at least a 2 from the power of p. We get at least 2 vp of x from the power of x. And then, you need to know something about p choose k, p choose 2, p choose 3, up to p choose p minus 1. All of these binomial coefficients are divisible by p. And you can think about that a little bit. Okay, so all of these other terms are divisible by larger powers of p. So if you have something that's divisible by a particular power of p plus some larger power of p times an integer, then the largest power of p dividing the whole sum is going to be the largest power of p dividing this first term. So we get vp of z minus 1 plus 1. And that proves the lemma. Okay, so now let's apply this lemma to z equals 1 plus p. So vp of 1 plus p to the p to the k minus 1 is vp of p plus k. We're just applying this straight out. And this is vp of p is 1. So this is k plus 1. Okay, so now what does that mean? That means that 1 plus p to the p to the alpha minus 1 is congruent to 1 modulo p to the alpha. You subtract 1, and you're asking for, does p to the alpha divide 1 plus p to the p to the alpha minus 1? And it does. So you put in alpha minus 1 for k, and you see that the largest power of p dividing this thing on the left-hand side is p to the alpha. But, sorry, this n should be an alpha. If instead you take 1 plus p to the p to the alpha minus 2, this is not congruent to 1 modulo p to the alpha. So the order of 1 plus p in z mod p to the alpha z star, it divides p to the alpha minus 1, but you raise this 1 plus p to the p to the alpha minus 2 power, and you don't get 1. So that means the order is exactly p to the alpha minus 1. Okay, so we've proven the first big part, that the CELO p subgroup of z mod p to the alpha z star is cyclic. Before moving on to do the rest of this proof, I'll point out that this lemma, this argument here, is actually really, really similar feeling to this thing that we did about writing 5 to the 2 to the alpha minus 2 as 1 plus some odd number times 2 to the alpha. So yeah, so you actually should be able to do the case where p equals 2, this previous case, to show the order of 5 in z mod 2 to the alpha z star using this lemma. But I thought it would be good to present sort of both of these approaches and let you compare them. OK, so I'll pause and erase, and then we'll finish this proof. Let's finish this proof that z mod p to the alpha z star is cyclic. We've already seen that the CeLO P subgroup is cyclic, so it's enough to show that the CeLO Q subgroup is cyclic for every other Q dividing the order of this group. So the idea is to consider this homomorphism from z mod p to the alpha z to z mod pz, which is reduction modulo p. Like if you have a residue class 5 modulo 8, that's giving a residue class 1 modulo 2, for example. So let's do this a little more carefully. Phi of what does an element of z mod p to the alpha z look like? Well, it's a coset of the ideal generated by p to the alpha in z. So it's a left coset of this ideal. So it's something like a plus the ideal generated by p to the alpha. You apply phi, and we're going to take what does an element of z mod pz look like? It's a coset of the ideal generated by p in z. So we're going to send a plus the ideal generated by p to the alpha to a plus the ideal generated by p. So this is reduction modulo p. So it's easy to see that this is a surjective ring homomorphism. This gives a surjective ring homomorphism of unit groups. So you look at what phi does. You restrict to the units. Units get sent to units. You get this surjective group homomorphism phi prime from z mod p to the alpha z star to z mod pz star. And now we know that z mod pz star is cyclic. All right, so what is the kernel of this? What is the kernel of this homomorphism? Well, the order is p to the alpha. Just by counting, this group has size p minus 1. This group has size p minus 1 times. The kernel has order p to the alpha minus 1. Because this group has size p to the alpha minus 1 times p minus 1, and this group has size p minus 1. So just by counting, you can see that the kernel has order p to the alpha minus 1. OK, so now let's take q to be a prime dividing p minus 1. And let's look at the CeLO Q subgroup of z mod p to the alpha z star. And now this maps isomorphically onto some subgroup over on the right-hand side here. Why? Because this group has order q to some power, and the kernel over here has order p to some power. So if q and p are different primes, the kernel can't intersect with the CeLO Q subgroup at all. So they have trivial intersection. OK, so that means first isomorphism theorem, you restrict to this subgroup, you're getting a homomorphism whose kernel is trivial. So it is isomorphic to its image over here. OK, but then if you have a finite abelian group that maps isomorphically onto a subgroup of a cyclic group, then the group that you were mapping had to be cyclic. Right? If you had like a copy of zq mod zq, that can't, zq cross zq, z mod qz cross z mod qz, that can't map isomorphically onto a subgroup of z mod pz star because z mod pz star is cyclic. So there is no subgroup isomorphic to z mod qz cross z mod qz. So the CeLO Q subgroup is cyclic. That's true for every prime q dividing p minus 1. We've already seen that the CeLO P subgroup is cyclic. And now we know that every CeLO subgroup of z mod p to the alpha z star is cyclic. So this group is cyclic.